All right, class, welcome to section 4.5, last section of this chapter. So we're just going to solve polynomial equations, so equations that some of them we could not solve prior. We can use our graphing calculator. Sometimes we won't have to. So let's see what the differences are, and let's get started. So it's a fourth degree polynomial equation, therefore I'm expecting 4 possible solutions. Not all of them have to be real. Some of them can be imaginary solutions, so we might get answers with eyes, okay? Some answers might be of higher multiplicity, so we might get an answer twice or 3 times, right? So that's what this story is about. Okay, so here it is. Solve the equation. Okay, so first things first, we always look, is there something we can factor? Because we've learned if we can factor, we'll get to the answer faster. So as you see, I already noticed that x is the greatest common factor, so therefore I get that out of the way. Okay, now that's better. Okay, so at least we will have one solution. X equals to 0 is a possible answer, right? Plug in 0 in all these places, you will get 0. And now we just need 3 more answers. So I am going to use my graphing calculator to find one possible answer. And again, these are the kind of values that I'm looking for. So P is a number that goes into 6. Q is a number that goes into 6. So any combinations of these numbers, 1 over 1, 1 over 2, 1 over 3, 1 over 6, 2 over 1, 2 over 2, and so on and so on. So I have the graphing calculator ready. I have all the functions in here. So let's graph this one. All right, so again, as you see, it crosses through 0. We already knew that answer. And then I see some more good ones. A good one that I'm finding is -2, so I'm going to try that. The others seem to be decimals. So I'm going to take -2, and I'm going to use synthetic division on -2, and again, the polynomial I still have to break down. So 6, 5, -17, and -6. Okay, bring down the 6 times -2 is -12. Add them up. -7 times -2 is 14. Add them up. -3 times -2 is +6. So success, we got a 0 remainder. So that means x minus 2 minus -2 is a factor. So -2 is a solution. Then what's the leftover polynomial is a 6x squared minus 7x and -3. So x plus 2 is going to give me an answer that says x equals to -2, and then I'm going to try and break this polynomial up some more. So you can use synthetic division if you want with other factors that you might see on the graphing calculator, or again, now that it's quadratic, hopefully we can factor it out ourselves. So numbers that multiply to 6 are 2 and 3. Numbers that multiply to 3 are 3 and 1. So remember, never pair up in a parentheses numbers with common factors, because that means there would have been a greatest common factor to begin with. Then I'll put a minus here and a plus here. So I'll get -9 plus 2, which is the -7 in the middle, so it's factored correctly. All right, and then the last 2 answers for these are that either 2x minus 3 is 0, which again, add 3, then divide by 2 would get you the 3/2. We saw the 1.5 on the graph, that's that one. And then 3x plus 1 is 0, which makes 3x equal to -1. Therefore, x equals to -1/3. So here are our 4 solutions to our 4th degree polynomial equation. And they're all real. And not only real, they're rational numbers, so no square roots left in them. All right, well, this is a big one. I do not see common factors, even though it is a 4-term polynomial. I already see that if I am trying to group them, I will not, there's no pattern in here. So I'm not going to waste my time. And again, I'm going to think about what kind of values might I possibly get. So P has to be a factor of 27, not 2. 1 times 27, I meant to say. And then 3 times 9. And then Q has to be a factor of 8, so 1 times 8, and 2 times 4. So again, any combination of these. Then I'm going to take my graphing calculator, and I'm going to graph this function. All right. So no matter how far out I zoom, I will only see one crossing point. So in other words, there's only one real solution for that polynomial equation. The other two must be imaginary. So as I zoom in more and more, I see negative 0.75. So negative 0.75, that's negative 3/4. So I definitely see that as one of my options, which makes me think that is a good possibility. So in other words, that I probably read correctly off the graph. So let's do synthetic division on that number. So I'll bring down the 8 times negative 3/4 is negative 6. Times negative 3/4 is negative 9, times negative 3/4 is negative 27 indeed. Okay, you can verify with your calculator. So this is what I have so far. X minus 3/4, then 8x squared plus 12x plus 36. All right. So I'm going to try and factor this if I can. It's quadratic. I definitely see 4 as a greatest common factor. And really this 4, as I explained earlier, is the one that combined in here would get me that really 4x plus 3 factor that we normally see when zeros or answers are rational. But either way, the reason why I also factored out the 4, which was the greatest common factor, is because even though I won't be able to factor this, I already know it. I'm going to get imaginary solutions. I saw that off the graph, so I won't be able to factor. But at least the coefficients I'm now going to use in my quadratic formula are going to be much smaller, so easier to work with. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a, which is 2. So that's going to be negative 3 plus or minus the square root of, so I have to see what 9 minus, that's an 8 times 9, so 72, so that's a negative 63 over 4. I'll make this shorter. So again, that's a negative 3 plus or minus I square root of 63 over 4. You can definitely still simplify this radical. 63 has a factor of 9, so you could throw out the 9 as the square root of 9 as an square root of 9 as a 3, and then just leave the 7 inside. So you can do that, but you don't have to. You don't need to simplify the radicals. That's all I'm saying. So this third degree equation had the one real solution we saw in the graph, right? Then we used that intersection point with the x-axis, and again looking at if that's a possible rational root indeed, so we don't have to waste our time trying. So -3/4, and you could have used -0.75 in synthetic division just the same. And then we knocked that out, and it was one of our zeros, one of our solutions, and the only real one. And then we were able with synthetic division to break that polynomial off, right, to see what the quotient is, or the leftover factor, and then solve that using the quadratic formula. Okay. So here's one more. Can we factor? Absolutely. There's a greatest common factor of x squared. So immediately we were able to take out two possible solutions. So x squared is equal to 0. That simply means x equals to 0. This is a 0 of multiplicity 2. So x is 0 and x is 0. These are two solutions that look exactly the same, right? Now, again, maybe I can factor this polynomial here, but the numbers are a bit too big. I could factor out a 2, by the way, so let's factor out the 2 as well. I'm going to take out the 2. I didn't notice that one at first. So 17, 2, so that's 6x, and then that's just the 20. So the advantage to this is, again, the numbers I'm going to use next in my quadratic formula are going to be much better. So here it is. So factorable or not, I don't really want to think about splitting. I can't even split the 17. So it might not be factorable, but no problem. It's quadratic, so I can solve any quadratic equation, factorable or not. So I'm going to get 4 times 17 times 20 is 1360, plus a 36. That's going to be a positive 1396. Okay, and then I'm going to check if that is a perfect square. I doubt it. So what's the square root of 1396? And I'm getting a decimal answer. So indeed, this is not a perfect square. And even though, yes, for sure, it has some perfect square factors, for sure, at least the 4 that I could throw out. But as I said, don't worry about simplifying the radicals. So here are my 3 solutions. One of them, oops, wrong one. One of them is 0. Actually, I should say 2 of them are 0. And then the other 2 are these irrational numbers. So they're real numbers, but they're irrational. So they're going to give me infinitely many non-repeating decimals if I try to graph this. If I put that in the calculator. So what I wanted to say is that, here it is. I'm going to graph this one next for you to show you what clues we would have gotten. See how 0 is a 0 of multiplicity 2, how the graph is bouncing off at 0? And these numbers are some weird value. Again, if you look in the left corner of the screen, you will see a 0.92244. The decimals won't end there because you're getting an irrational number. So you'll have infinitely many non-repeating decimals, right? And we got those off. Yep, the graph is going to go. Eventually it's going to turn. So yes, it's a 4th degree polynomial function. It does have 3 crossing points. One of them is a double zero. So again, fourth degree polynomial, we expecting 4 zeros. We got them. At most 4 zeros. At most 3 turning points. We saw those. And the end behavior should be that of a quadratic function. So that's what we saw. All right, next one. Again, always think, could you factor? Do you see in many of these cubic equations will have 4 terms. If you group them and try factoring by grouping, again, first of all, is there a greatest common factor? No, there is not. If you try factoring by grouping, do you notice a pattern? Absolutely, for this one. So from the first 2 terms, I'm going to factor an x squared, then I'm left with an x minus 1, plus from the last 2, I factor out a 7, so I'm left with an x minus 1. And for factoring by grouping to work, you can definitely, you definitely need this parentheses to look exactly the same, and it does. So here are my 2 answers. Either x minus 1 is 0, which makes x equal to 1, or x squared plus 7 equals to 0. So let's solve this quadratic equation. And if you remember, in the chapter of quadratic equations, we learned what we call the square root property. So thank goodness we reviewed that. So again, remember, you get 2 solutions because you're solving a quadratic equation. So you must get 2 answers, therefore the plus or minus. The square root of -7, that's another thing we discussed. And then that has a negative inside the square root, which spits out an I. So these last 2 are imaginary solutions. So easily, if you can factor, we could get done immediately. I'm just going to show you this one as well. I have it listed here. If you didn't notice the pattern and you didn't factor by grouping, but relied on your graphing calculator, no problem. Again, as you see, there's only one crossing point, and that would be at 1. So you would use synthetic division with a 1, and then your synthetic division would leave you with an x squared plus 7 for your quotient, and you'd continue solving that. So here's one more. And again, I kind of notice a pattern, 2, 3, and 8 and 12, if you factor out a 4, would get you a 2 and a 3. So let's see. Factor out the x squared times 2x minus 3 plus, from 8 and 12, as I said, factor out a 4 times 2x minus 3. So as you see, you do have the common factor of 2x minus 3. So just like the problem above, we will get one real solution, which is 1.5 or 3/2. And we will get 2 imaginary solutions. So if I square root this equation here, it's going to get me the x is, do not forget about the plus or minus, as you do need 2 solutions. And what is the square root of -4? Again, we reviewed this in 3.1. The negative is an I, and the square root of 4 actually is 2. So here are my other 2 answers. So 1 real, 2 imaginary. Okay. As a matter of fact, if a polynomial equation with real coefficients, so you're not going to see i's to begin with, if it has imaginary solutions, then they always come in pairs of complex conjugates. So in other words, you're never going to get just one imaginary solution. You always do get 2. And so what happens is the 2 answers are always going to be plus some a plus bi and some a minus bi. In this case, it's 0 plus 2i and 0 minus 2i. or 0 plus I radical 7 and 0 minus I radical 7. There is no real part in either one of these. So the point is you always get them in pairs. Because of the plus minus also that comes out of the quadratic equation, and that always is in front of the I term, if anything. So in other words, if A plus BI is a solution, then A minus BI is a solution. That's an important fact. Okay, so only again when solving equations are we looking at the imaginary solutions, because to graph a function, remember, you cannot put imaginary solutions on the real number line. So the last few questions here are giving us a 0 and are asking us to find the remaining zeros. We did this problem in the last section, but the 1 0 we were given was real. Here, this time, the zeros I'm giving you are imaginary. So because of this, because we do know one imaginary solution, then for sure we know that its complex conjugate, negative 2i, is also a solution. All right. So remember what we said. If, let's say, a number k, so 2, is a solution, then x minus that number is a factor. So I'm using the factor theorem. So I know 2i is a 0, so x minus 2i is a factor. And then negative 2i is a 0, so x minus 2i is a factor. So those are going to be two factors for this polynomial equation. Now, it is not easy to use synthetic division with imaginary solutions, with imaginary zeros, right? So in other words, don't try and do synthetic division like we did before. We know negative 2 is a 0. Great, I can do synthetic division on it. With i's, it's not going to be that easy. So one easy way to do that is multiply these two factors together. And see what we get. We'll get an x squared. These guys are gone. And negative 4i squared. Remember, I squared is negative 1 times negative 4. That's going to be a positive 4. So there you have it. By the way, I'm starting with a question we just did backwards. We solved the equation x squared plus 4 is 0, and we got answers plus minus 2i, right? So again, if plus and minus 2i are the solutions, going backwards, we found that x squared plus 4 is our polynomial equation. Now, I just still need to know what else do I multiply this by? What's the quotient, right? What's the leftover factor? So therefore, we have to use long division. We can't use synthetic division on such polynomials. But remember, that's also why we practiced at the end of 4.3. We practiced long division. I said we're going to need these coming up. So here it is. It's what we needed. And also remember what I said. If a term is missing, see how there's no x in x squared plus 4? We're going to fill it in with a 0 coefficient. Okay. So let me erase this so I can have, I'm just going to write 0. Okay, so let's do long division. X squared goes into 3x to the 4th. How many times? We need a factor of 3, and we need 2 more x factors to get from 2 to 4 x's. So 3x squared times x squared is 3x to the 4th, plus 0x to the 3rd, plus 12x squared, minus, minus, minus. So I'm going to get an x cubed minus 10x squared, and then bring down that 4x and play the game again. X squared goes into x cubed how many times? Well, we just need one more x factor. So x times x squared is x cubed plus 0x squared plus 4x. Subtract everything. So these guys go away, negative 10x squared. And then 4x minus 4x is nothing, but because it's in the middle, I'm going to write 0x and bring down the negative 40. Okay, so x squared goes into negative 10x squared. I just need a negative 10 factor. So again, remember how these powers also have to go down by 1. So negative 10 times x squared is negative 10x squared. Negative 10 times 0x is 0x. And negative 10 times 40 is negative 40. So as you see, the remainder here is 0 as promised. So the leftover polynomial here is a 3x squared plus x and minus 10. So the question is, could we factor this further? So I'm going to try 3 and 2. Factors of 10 are 2 and 5. No, it doesn't work. Nope. Oops, not 3 and 2, 3 and 1. That's why. Numbers that multiply to 3 are 3 and 1. Now, numbers that multiply to 10 are 5 and 2. And now it works. So I'm going to get a negative 5x plus 6x is the positive 1x I need in the middle. Okay. All right. So one possible or two possible answers are the plus minus 2y that we were in fact given. Then the leftover solutions are both real, 5/3, and negative 2. And again, 5/3, because when you set the 3x minus 5 equal to 0, you add the 5, divide by 3. Okay. Here's another one. Again, if you would have graphed this polynomial equation or polynomial function, you could have seen the negative 2 and the 5/3 solutions, possibly, and come back through those to find the plus minus 2i. It's kind of hard to guess the 5/3, by the way, off the graph. So it would have been a bit difficult to see that 0. And then with just 1, it would not have been enough. You definitely need at least 2 to get it down to a quadratic that you can then solve. So we were given the imaginary solutions. So if 2 minus I is a 0, then 2 plus I is also a 0. So therefore, x minus 2 minus I and x plus 2 plus I are 2 of my factors, right? And then I just need to find the leftover factor later on. Okay. So those are 2 of my factors. Again, if one number is a 0, then 2 minus, thank goodness I looked again, minus that number is a 0, is a factor. So 2 minus I is a 0. Therefore, x minus that is a factor. The reason why I put them again in parentheses, because subtracting is always tricky, is you must change the signs. And if you don't, you are wrong and you're going to get the wrong answers. So I'm going to distribute all this, and it's going to take me a while. Again, you need to make sure x times all of them, 2 times all of them, I times all of them. So you will get 3 times 3, 9 different terms. Okay, but combining them makes a whole bunch of them go away. You have, yes, red, ix and negative ix, 2I and positive 2I go away. By the way, negative I squared is -1, with the extra minus that makes it a +1. So all of this factors into an x squared minus 4x and plus 5. 5 because the 4 plus 1. Okay, so I still need the leftover quadratic in order to finish solving this equation. So I'm going to have to use long division to finish up this problem. Okay. So I'm making myself a little bit of room here. So how many times does x squared minus 4x plus 5 go into x to the 4th minus 4x cubed plus 9x squared minus 16x plus 20? So x squared goes into x to the 4th how many times? That's an x squared. Times x squared is x to the 4th. Times negative 4x is negative 4x to the 3rd. Plus 5x squared. When you subtract these, the x squares are gone. But so are the negative 4x cubed. So because they're in the front, I don't need to write that 0. However, because we lost the first 2 terms, we get to bring down the next 2, so 2 at a time. Because I need a 3rd degree polynomial, a 3-term polynomial to go into a 3-term polynomial. So to go from x squared to 4x squared, I still need a factor of 4. And here it is. 4 times x squared is 4x squared minus 16x and plus 20. So perfect. There is no remainder as promised. Therefore, this polynomial here I'll write it one more time. My initial equation factors into these 2 quadratic factors. The first one, we already know what kind of answers we get. We get 2 plus or minus I. And we know we get those answers because that's how we found this polynomial. By multiplying the x minus 2 minus I to x minus 2 plus I. So we knew the zeros, that's how we made up the polynomial. The x squared plus 4, we also solved this one a couple times in this section. The solutions to it are also imaginary, and they're plus or minus 2i. So we're getting actually 4 imaginary solutions for this 4th degree polynomial. So we're getting two groups of imaginary solutions. So no real answer. Let me see if I have that one even written down. No, I don't. I'm not going to type it in, but if you're going to type it in and graph it, you will see that it does not at all cross through the x-axis. Okay, so there are no real solutions, so you couldn't have even done this problem with synthetic division, okay, and knock 1 0 out at a time. So yeah, the only way to solve this would be if you already knew at least one imaginary solution. Okay, now this is a 5th degree polynomial function. We will at least get one real solution, and the reason why I'm saying this, because of the 5 solutions only 2 at a time can be imaginary, right? And so therefore one of them is going to have to be real. Okay, so we are given one imaginary solution, so therefore its complex conjugate is the other solution. So if I is a 0, then x minus I is a factor. And so is minus I. So if we multiply this out, we're going to be done super fast, because you're going to get an I squared and minus x squared and minus I squared is a positive 1. So yeah, very similar. The x squared plus 4 gives you plus minus 2i. The x squared plus 1 gives you plus minus 1i for answers. Now, let's find the leftover polynomial. So one more long division. Okay, so x squared goes into x to the 5th, x cubed times x to the 3rd times x squared is an x to the 5th, plus 0 x to the 4th, plus x to the 3rd, and then subtract all of these. So you're left with, these are gone, so negative 1x to the 4th, plus 4x to the 3rd, bring down the negative 5x squared. So you'll have a minus x squared. So negative x to the 4th plus 0x to the 3rd minus x squared. So we'll get a 4x cubed minus 4x squared, bring down the 4x. So I'll do this one more time. So we'll get a 4x. Again, the powers go down. So 4x times x squared is a 4x cubed. 4x times 0x is 0x squared. 4x times 1 is 4x. Subtract. So we'll get a negative 4x squared plus 0x's, and finally bring down the negative 4. So one more time, x squared goes into negative 4x squared and negative 4 times. Yeah, negative 4x squared plus 0x and minus 4. So when we subtract these, we're going to get no remainder. Okay. So the leftover polynomial here is x cubed minus x squared plus 4x and minus 4. So again, you can use your graphing calculator from here, see what else happens to this leftover polynomial if you can break it up some more. This one's very similar with the problem we did up above, which gave me, I see the pattern, right? Remember we did the one with the 7 further up? It's the same exact one. So I definitely see a pattern, and I'm going to factor using factoring by grouping. So I have an x squared coming up from these two terms. These last two have a 4 in common. Okay. So then that factors into x minus 1 and x squared plus 4. That's just for this polynomial here. I'll write this one at the front for completion. So this is what my initial polynomial here factors into. A quadratic, a linear, and a quadratic altogether adds up to a 5th degree polynomial. So here are my solutions. This one's plus minus 1i. We already know that because that's how we found those answers. X equals to 1 is the one real solution, and we've had this one many times already before. I'm not going to go through the trouble of solving it again, but plus minus 2i or the other solution. So even though this was a 5th degree polynomial, we did get 5 answers, not all of them real. As a matter of fact, 4 of them are imaginary, 2 groups of 2, and 1 of them is real. So if you graph this polynomial function, not much is happening. 5th degree, not many turning points at all. As a matter of fact, it doesn't seem to turn at all. It kind of like almost looks like it evens out, but it doesn't completely turn. This is increasing on the whole number line, and there's only one crossing point between the negative and the positive side, and that would be at the 1 that we got. Okay, so here it is. So yes, for these kind of equations, to come up with all the solutions, if you had 4 imaginary solutions, you just can't find them unless you are given one group. So yeah.